Okay, continuing on. Whenever we have a temperature change, we're going to experience a couple of different things. It's temperature change. Of course, the temperature is proportional to the amount of thermal energy that's in a substance. So the more thermal energy, the higher temperature you have. As you have changes in temperature, you will change phases. And of course, the phases, from, I don't know, middle school, elementary school, as you have these temperature changes, you will move through the phases going from a solid like ice to a liquid like liquid water to a gas. We also have another phase, which is called a plasma. We're not concerned about that. But a plasma, if you're curious, is an ionized gas, so where the all the electrons have been stripped off the gas molecules or atoms. So anyway, we will move through these uh, these phases, going from solid, liquid to gas. If I let's see, I have a plot here. What's this for just a second? So let's see, I couldn't find the plot, but I can draw it pretty simply. Let's plot the temperature of a substance versus the energy. So let's imagine that I start with, ice, water ice. It has a temperature below 0 degrees Celsius or 32 degrees Fahrenheit. As I add energy, thermal energy to that ice, it will increase temperature until it reaches a temperature right here of 0 degrees Celsius. At which point you have to put in additional energy to change the ice from ice into water. So as we continue to add energy, the temperature of the ice will remain constant as we convert. So in this place right here, we are converting ice to water. Because it requires a certain amount of energy to take those ice crystals and tear them apart and create this liquid water. And then when it's all converted to water, it begins to increase temperature again. Here I have water only until I get to a point where I reach a temperature of course, 100 degrees Celsius. And at the 100 degrees Celsius, then we will continue adding energy in, continuing to add energy. Here I have water plus steam. But notice that both the water and the steam are at 100 degrees Celsius. So the point is here that when you reach the boiling point or when you reach the freezing point, it's not all of a sudden that your substance either turns to a vapor or a gas or a solid. You can have 0 degree water. In fact, you do every day when you have ice water. You have the ice and the liquid water. Those are pretty much in thermal equilibrium at the same temperature. So you have ice at 0 degrees Celsius and water that's 0 degrees Celsius. Well, why does that water not convert into ice? And the reason is it has too much energy. That you need these extra bumps of energy like here and here in order to convert your liquid or your solid into convert your solid into a liquid or your liquid into a vapor. Now, once you get up here, after you convert it all to steam and you continue adding energy, then you continue to increase the temperature of the steam. So you might wonder, well, does water that's 100 degrees Celsius or steam that's 100 degrees Celsius, which is more potentially dangerous to us? Well, the steam is more potentially dangerous because it just has a lot more energy. I've added a lot more energy. Even if I'm looking at the steam that's 100 degrees Celsius, it has a lot more energy than the water that is 100 degrees Celsius. This extra energy that's required to convert ice to water is called the latent heat of fusion. That is the extra energy required to convert ice into water or any solid into a liquid. And this extra energy that's required to turn the liquid into a gas is called the latent heat of vaporization. This amount of energy, which remember heat, we're using Q to represent heat is equal to the mass of your liquid, in this case, times the latent heat of vaporization. We usually use an L and a subscript V, latent heat of vaporization. Here, the energy required to convert the ice to water is equal to the mass of the ice times the latent heat of the fusion. Or if we're going from water to ice, that's the amount of energy that you need to take away from the water in order to convert it into ice. We also can describe the amount of energy required to raise the temperature here. This is equal to Q is equal to M times C times delta T, where here M is the mass. C is something that we've already seen, I believe. No, maybe we haven't. C here is the specific heat. Let me go down. The specific heat of a material describes the amount of energy required to raise that material's temperature by a certain amount. Let me repeat that. It describes the amount of energy required to raise the temperature. Required, it's an abbreviation there, to raise the temperature of the substance by a certain amount. So when we're talking about thermal energy and as we introduce it to a substance, we have a couple things we talk about, just to recap. As I add thermal energy into a substance, I can increase its temperature, and this describes the amount of energy required to increase its temperature. So if I have a certain mass of material with a certain specific heat, and I want to raise its temperature a certain amount, I take the product of those three, and then that tells me how much heat is required, how much thermal energy is required. By the way, that specific heat, you probably have an intuitive sense of it. Like, for example, consider two materials. Consider wood and consider copper or any other metal. Which of those would you think have the higher specific heat? Which of those require more energy to raise the temperature of that substance by a certain amount? Well, of course, it is what? It's wood. Wood requires a lot more energy to raise its temperature. You know this because, like, for example, if you have a fire and you stick your marshmallow fork in it, then that fire will transfer its energy to you more readily than it would if it were a metal stick. The other thing is that if I'm changing between phases, solid, liquid, and gas, I need an extra amount of energy. I need that latent heat of fusion to go from ice to water. In order to go from ice to water, I have to add in that amount of energy, which is equal to the mass times the latent heat of fusion, in order to convert from ice to water. Or if I want to go from water to ice, I have to take away that amount of energy in order to convert it into ice. And similarly, between the liquid and gas stages, I need this heat of vaporization, which is equal to the mass times the latent heat of vaporization, M times LV. That's the amount of thermal energy that's required in order to convert a liquid into a gas. The whole study of this is called calorimetry. When we're in class, I'll share with you a clip about calorimetry and how they use the process of calorimetry in order to determine the energy content of food. It's fairly interesting. They take a little piece of food and they put it into this calorimeter and they basically blow it up. And then they measure the change in temperature, because the energy that's in that food will actually, cause a change in temperature. And when they measure that change in temperature, they can determine what is the energy in that little bit amount of food. All right, one more thing that I want to share with you before we call it off here is there are different ways of transferring energy. Let me pause here for just a second. There are different ways of transferring energy. There are three ways. We have conduction, we have convection, And then we have radiation. Let's go back to our campfire. Here's our campfire, and here we are. We're standing here, and we've got our fork sticking in the fire. There are several different ways that energy is being transferred from the source of heat, which is the campfire, to you, which, you're the person receiving the heat. You have a couple of different ways. First is conduction. This is conduction right here. I have a substance that is touching the source of heat. Conduction is conducting from the fire to you, so that is conduction. The second is convection. Let's imagine that there is a wind blowing through the fire. That is convection. So it is blowing heat from the fire onto you, like a convection oven. A convection oven has a fan inside it that causes airflow. So for convection to occur, you need the flow of a liquid or gas. And that helps to transfer the heat from one substance to another. And then the third thing is radiation. The fire actually gives off infrared radiation, which travels through space to you, and you feel the heat from it. We've all experienced those different forms of radiation, or those different forms of thermal transfer or heat transfer. Now, regarding conduction, if I have two substances of different temperatures, let's say that I have a substance here, A, have a substance here, B, they are connected by a certain material. This material has a length, D, it has a cross-sectional area, A, and then we also have a difference in temperature between A and B. I can calculate the rate of conduction like this. Q over T is my rate of conduction. Remember, this is energy, so calories per second or joules per second. How much energy per unit time is equal to K, I'll explain what that is, A delta T over D. D is the length of this material that is connecting these two bodies. So it's like the marshmallow fork, for example. If you have a longer marshmallow fork, you're not going to transfer as much heat. If D increases, Q over T decreases. It's an inverse relationship. If the area of my marshmallow fork gets bigger, if A increases, Q over T also increases. There's just more area for this, or more material for the heat to transfer through. Now K is something called the thermal conductivity. In that Vaporization video, he talked about thermal conductivity and what that is. Some materials just transfer heat more readily than others. Let's go back to our copper and wood. Which of those transfer heat more rapidly? Well, of course, copper transfers heat more rapidly. You stick a wooden stick into the fire, it's not really going to transfer heat very quickly. But if you stick a metal rod into the fire, it'll get hot really quickly and you'll have to drop it. All right. For those with a higher K value, you will also have a higher rate of thermal transfer. So you need to know those three ways of transferring radiation, the conduction, convection, and radiation. And then also regarding conduction, know how it depends upon these different variables. The thermal conductivity, the area, the distance T. Oh, and then also, that rate is also dependent upon our difference in temperature. If I have two substances that are practically the same temperature, they're not going to transfer heat that quickly. But if I have two substances that are hugely dissimilar or different temperature difference, then they will experience a greater rate of thermal conduction. You don't have to calculate anything for this for the exam, but you will need to know how it depends, the rate of thermal conduction, Q over T, how that depends on these four variables, K, A, delta T, and D. You have the equation, so if you're clever at reading the equation, then you'll see anything that happens in the numerator has to happen over here. anything that happens in the denominator, the opposite has to happen on the other side. That's really what I'm getting at, is that you're able to look at these equations and see the relationship, and not just see a big jump in numbers, which is what most people see. But of course, you're not most people. You're sharp folks. So anyway, we'll stop there and pick up in class tomorrow.